Here in chapter 12.3, we study infinite limits. So what is an infinite limit? Well, here is our textbook definition. Suppose f is defined for all x near a if f of x grows arbitrarily large for all x sufficiently close but not equal to a. We write the limit of f of x as x approaches a is equal to infinity. Let's break this down. Now remember, limits tell us about the behavior of our graph. What happens to the y values as x gets closer to some number? Here we are saying if our y values are getting larger and larger and larger as x gets closer and closer to a, then our function is increasing without bound and those y values are approaching positive infinity. Therefore, the limit of f of x as x approaches a is equal to infinity. Similarly, if f of x is negative and grows arbitrarily large in magnitude for all x sufficiently close but not equal to a, we write the limit of f of x as x approaches a equals negative infinity. This is saying if our y values are becoming smaller and smaller and smaller, right? Our graph is going down, 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 down. We're getting larger in magnitude for negative y values. As x gets closer and closer to a, our y values are approaching negative infinity. Therefore, we write the limit of f of x as x approaches a is equal to negative infinity. All right, so we've discussed infinite limits a little bit before when we talked about their graphs and seeing them on a graph. And we're going to cover that again. But one thing to make note of is that in both of these cases, all right, we say the limit does not exist. That's very important. The limit does not exist because we are not approaching a unique number. Positive infinity or negative infinity, they are not real numbers. Therefore, the limit does not exist. That being said, okay, we need to be specific. Do not simply write dne. Make sure you are specifying whether or not the limit is equal to positive infinity or negative infinity. So let's look at some graphical interpretations of infinite limits. Use the graph to evaluate the following limit. Here we have the limit as x approaches 1 from the left of our function f of x. Here's the given function f of x. So what happens to the y values as x gets closer and closer to 1 from the left-hand side? Well, as I'm traveling along my curve and my x values are getting closer and closer to 1, my y values are going up and up and up. They are increasing without bound. They are approaching positive infinity. And again, as we said, because positive infinity is not a real number, we also want to specify dne. Infinity dne is our answer. The limit as x approaches 1 from the right. Well, I'm traveling along my curve as my x values are getting closer and closer to 1 from the right-hand side. Notice my graph continues to go up and up and up to positive infinity. And because positive infinity is not a real number, we write dne again. And those are our left and right-sided limits. Now let's evaluate the limit of f of x as x approaches 1, the general limit. Well, because the left and right side limits are the same, the general limit is the same answer as well. Our answer is infinity dne. One thing to make note of that is very important here is that we have the presence of a vertical asymptote at x equals 1. All right, here at x equals 1, the vertical line x equals 1 is a vertical asymptote. Let's look at another one. Use the graph to evaluate the following limits. The limit as x approaches negative 3 from the left of f of x. Well, as I'm traveling along my curve and my x values are getting closer and closer to negative 3 from the left, my y values are going down, down, down to negative infinity. Therefore, we write negative infinity, comma, dne. The limit as x approaches negative 3 from the right. Well, as I travel along my curve, and my x values are getting closer and closer to negative 3 from the right, my y values are going up and up and up. Therefore, our limit is equal to positive infinity and dne. And now we have our general limit. The limit of f of x as x approaches negative 3. Well, in this particular case, the left limit is negative infinity and the right side limit is positive infinity. Because the limits from the left and right are different, we simply put dne. Again, note that the limit as x approaches negative 3 from the left and right are different. Therefore, the limit as x approaches negative 3 does not exist. That being said, what do we have at x equals negative 3? Well, x equals negative 3 is another vertical asymptote. All right, so yes, there is a correlation between infinite limits and vertical asymptotes. This is our calculus definition now. If the limit as x approaches a of f of x equals positive or negative infinity, or if the limit of f of x as x approaches a from the right equals positive or negative infinity, or if the limit of f of x as x approaches a from the left equals positive or negative infinity, then the line x equals a is a vertical asymptote of our function. Okay, so if we are evaluating a limit as x approaches some real number a, and we get an infinite limit, meaning our answer is positive or negative infinity, that means the line x equals a is going to be a vertical asymptote. And that's just what we saw in our first two examples with our graphs, right? We had a vertical asymptote here at x equals 1, and in our second graph, we had a vertical asymptote at x equals negative 3. All right, so very important relationship. If we are evaluating a limit as x approaches a real number a and we get out an infinite limit, meaning the answer is positive or negative infinity, then we have a vertical asymptote at x equals a. So there you have infinite limits and identifying infinite limits from a graph. In the next video, we'll talk about finding infinite limits algebraically.